We're going to have two presentations focused on marine geology and marine survey from me and Alessandra. Okay, and then Vera will explain to you how you can create the story maps. And then you will stay here and work as long as you want, because we have your presentations on Saturday at noon. Okay, so some of you, we heard some complaints, soft complaints, okay, that we didn't have time to process the data and start working your story map. So today you have the time to do that, and also tomorrow, after 1 o'clock, you will be free. You will be free to go around to CER, of course, but then come back and work here. Okay, so you have almost 1 day for your work. Okay, so I know that except of the Greek students, that all of them, not most of them, all of them are oceanographers. They are not familiar with some technical, okay, details. So me and Alessandra are not going to be focused on how these equipments are being working, but you need to know about the offshore geomorphology. And in Portsmouth, we played with the students. We saw them a map, and they identified, yes, my husband, and the kid, and they identified all the geomorphological features offshore. So we can also do that, because I know that you learn about active fault zones, submarine volcanoes, and so on, and you don't know what are these features. Okay, so we will try to explain. Okay, this is the underwater survey. This is the slide that you can show that definitely for underwater survey we need a vessel, any kind of vessel. For the deep survey, for surveying the deep waters, definitely we need a larger vessel. But if we want to have to explore the coastal zone, we can also rent a Zodiac or a smaller boat. And we have some different equipment using our seismic source. And this is how we are doing the seismic survey. So we explore the layers, okay, the stratigraphy below the seafloor. Or we are using also robots like AUV and ROV. You have seen the small ROV. Or the first things that we are doing, we are using multi-beam systems, and we explore the map, the seafloor, and we are creating some SWOT maps. Or there are some other techniques and some other equipment that we want to see only few meters or only few centimeters above the seafloor. And these are the systems that we use, especially on the ports or from an archaeological point of view, and so on and so on. So, the first thing, once upon a time, or only the sailing boats are using this, they use single beam systems. I'm going to give you this presentation, okay? So you can read everything. That's why I wrote down all the details in order to have the chance to read it when you have the presentation. I'm not going to read everything, okay? That's for sure. But it was my intention to give you the presentation, then you can also read in detail of what we have written. So most of the time, once upon a time, okay, we use single beam system. Okay, using only one transducer, and that has created a single narrow cone. You can see that. So the mapping that we did, we mapped the area just in a line. So this technique, this single beam system, also maps the depth, okay, in a line, and produced this kind of maps, draft maps. But if you go closer, you can see that on this map you have only single depths. Okay, this is an old map of Hydrographic Institute of Greece. Okay, and this is the area of course research. And also they created. You can also have some bathymetric profile just in one line. Okay, so this is the most important. This is a single narrow cone of energy. Okay, directed downward toward the seafloor, providing a single depth measurement for a location. So we collected single depths. Okay, these are the old bathymetric maps. The most important is that what we did is we tried to measure the water depth. How it is calculated. The water depth is calculated by using the travel time of the immediate pulse, and how long did they take the sound wave to travel from the transducer to the seafloor and back. So we measure the two-way travel time, okay? And we say that the velocity, the speed of sound in the water is almost, okay, 1,500 meters per second, and then divided by 2, because the sound needs, okay, some time to go down, and exactly the same time to go up, okay, and to be received by the transducer. Okay, so, but now we are using the multi-beam systems, and we map the seafloor in very detail for seabed mapping. It has been developed in the early 1960s. Okay, so what the multi-beam equipment is doing, the multi-beam emits sound waves in a fan cell. This is completely different from the previous version of the single beams. Okay, in a fan cell, provided a wide coverage of the bottom. So if you have a multi-beam system, okay, and the ship is moving, you are mapping the seafloor, okay, covering a larger area. Okay, so you are covering a larger area, and you are collecting thousands of depths. Okay, not only single beams, not only single depths. Okay, so what else? We are going to finish this problem because the presentation. Okay, this is an online video, but I will send you the link. Now it's not working because the internet connection is not so good. But why I'm doing this? This is a conventional bathymetric map. So we collected single depths using the single echo sounder system, and you can see the seabed morphology, and you can compare how detailed is the seabed morphology of this particular area, because even though you can understand that these are two sedimentary basins, submarine basins, but using the multi-beam system, you can identify more morphological features. Okay, so I did that on purpose. I processed the data of the single beam, and also we processed the data of the multi-beam just to see the difference between the two systems. For general point of view, you can use the maps like this, just to identify where are the basins, where are the ridges, where are the canyons in general. But if you want to map the seafloor in more detail, okay, and recognize all the seabed morphology, you need to have multi-beam systems. And I will show you in more detail what other things we are using. Okay, so, for example, this is the bathymetry. This is multi-beam system, and this is the bathymetry in the Galapagos Islands, bathymetry in 2015. Okay, this is 1 kilometer grid resolution. This is 10 meter grid resolution. Okay, so you can see the difference. Okay, you can understand that even in this, there are some ridges, okay, on the seafloor, but you need to map the seafloor in detail just to identify the geometry of these ridges, the geometry of this cone. So this is 1 kilometer grid resolution. What we are doing, we are split up the seafloor in cells. So the dimension of the cell here is 1 kilometer, 1 kilometer, 1 kilometer. The dimension of the cell here is 10 meters. So in 10 meter, you are collecting more depths, more single points of depth. That's why you have a better resolution map. Okay, what else we are doing? We have many different multi-beam systems, multi-beam echo sounders, and of course lots of different vessels. But we need to know the frequency, the operational depth, the swap width, and horizontal and vertical resolution in order to choose the proper equipment so as to map the seafloor. The main rule is that if we want to have large depth, if we are mapping large depth, we have large angle, but big footprint is this. Okay, if you have big footprint, you have less resolution. And if you are mapping the seafloor of Atlantic Ocean, of course, you cannot map the seafloor using a very narrow footprint because you are going to need many days. Okay, and believe me, this is rating a vessel is very expensive. Just to have an idea, is that the Greek vessel, you can rent the Greek vessel very cheap, only 15,000 per day. But the German one, or the Irish one, or the UK one is more than 50, 75. The seismic vessel that I'm going to show you, it was 150,000 per day. So you need large amount of money, okay, to do the survey. So if you want to map Atlantic Ocean in general, you are going to use these multi-beam systems that they have a big footprint, less resolution, but you will cover more area. If you want to map an area very close to the coastline, and you need to see the morphology of the coastline, definitely you need to have small depth, you need to have small footprint and high resolution. So it depends on what you want to do. Okay, and of course the money that you have. Okay, this is very important. Okay, it's not so. It is very difficult to do the acquisition because the technical persons, most of the times we are the technical persons, okay, except of the scientists. We are doing the multi-beam calibration because we need to figure out some motions, the motions of the vessel. This is roll, pitch, and yaw. These are technical stuff, but it's not so simple to map the seafloor. It's not just, okay, we press the bottom and then suddenly the ship will start mapping the seafloor. It's not this way. Okay, we spend almost 1 day to calibrate the multi-beam system. And of course, we are using GPS, Global Position System, GPS, because every single depth has coordinates. Okay, so we need to know where we are. And also what we are using CDD. So the CDD is conductivity, temperature, and depth. Okay, so we are using to measure the sound velocity, because if we are collecting wrong sound velocity and we need to map this area, we can create very easily, okay, some channels or ridges on the seafloor, even though these are not existing. What I'm trying to say, even though I know that this is very difficult to understand, is that you need to calibrate the system and also to import some external data like the GPS and CDD on the multi-system and then start mapping the seafloor. It's not so simple, okay? Even though the results you can see as one and say, oh, okay, that's good, it's not so simple. So the acquisition, we need powerful computers, okay, to receive all the points, the depths, okay, and this is, we have produced this diagram just to show you how many parameters are needed to map the seafloor. And collecting, how we collect swath data. Most of the times we are doing some lines, parallel lines, okay, in order to cover the area, and we are starting with the parallel lines, and then we map the area, and then you see we fill the gaps. But if you see, this is the North Aegean Sea. If you can see on this on the screen on this slide, you will see that most of the sometimes you have very narrow lines. The line is is parallel, but very close to each other. So here the depth is very shallow. So you need to have more lines to map the area and to have a full coverage of the area. But here the depth it's almost 2,000 meters. We don't know that, but we know that. With the biggest depth, okay, here you don't need so much coverage, and you can do less parallel lines. So it depends, okay, on the depth, on that. And okay, so you have the data. Okay, you collected the data. Now you need to process the data. This is another procedure because processing needs lots of time. Believe me, lots of time. If you are asking the Greek students, they can tell you that they spend 2 or 3 months or more to process the data. It's a very difficult procedure, okay? Because you need to produce a detailed SWOT map without wrong beams, without wrong depths. Otherwise, your interpretation will be wrong. Okay, so you need to be extra careful. So we are using, most of the time we are using MB system. This is the open software, so you can download MB system. This is in Linux and also in Windows environment. And you can see that, for example, okay, you need a research vessel, multi-beam system, data acquisition, you collect the data, so you process the data, you create, for example, a grid cell of 50 meters. Most of the time, when we are doing the mapping, the grid cell is 50 meters by 50 meters, okay? And then you can produce the mapping ArcGIS or GMT or whatever you like. So, now, these are some examples of the processing of the navigation. These are some screenshots of how we are doing the processing. You can see that if you collect the wrong sound velocity profile and you just plot the data, you will see that, okay, these are the lines, but here are the wrong beams. And if you clean the data, like this one, you clean the data, you can create a nice bathymetric map. Just see the previous one. Okay, no, sorry. Look at this. Okay, you can understand that this is the basic. Okay, the colors. We use blue colors, dark blue or light blue, for the deepest part, and orange, yellow for the shallowest part. Okay, just to have an idea of what colors we are using. So you can see here that these are the wrong beams. But if we clean the data, the map that we are going to produce, okay, this is a basin and this is a slope. And if you have very dense isobars, that means that you are a very steep slope. It's exactly the same with the topography, the onshore topography. Okay? Exactly the same technique for the interpretation. Also, this is the way how we are cleaning the data. This is the IP system. So we clean the outer bins, okay? We delete the outer bins because most of the time are wrong. And also you can clean the data using some 3D software, okay? So you can see the seabed morphology and you can click on that and delete all these wrong, you can see all these wrong bins, okay? That needs lots of time, Okay, while we are doing the mapping, we also, except for the geological interpretation, we map the seafloor in order to identify shipwrecks, for example. If you want to map a shipwreck, you need to have a multi-beam system giving you a high resolution maps. Otherwise, we cannot find a shipwreck. Or, these are the most modern, okay, ships that have been sunk, okay, with some particular method of the multi-beam systems. Or, you can also map very narrow areas, like the Isthmus of Corinth. The depth is almost 9.2 meters. And here you can see the very steep slopes, and here is a huge landslide. Here. It's a huge landslide. So we use that shallow multi-beam systems with very high resolution. Or you can map an area and then you merge the onshore and offshore data in order to produce synthetic maps. This is Niceros, this is the other volcano that I told you. Just think about that. This is Santorini. Santorini looked like before the Minoan eruption. It was round. You have the caldera. Here is the caldera. It was dry, without water inside. Okay, and the subaerial vents were somewhere here. So Santorini has exactly the same geometry and size of Santorini before the Minoan eruption. Okay, before the Minoan eruption. The last eruption here is 1888, okay, 1889, but we didn't have lava that came out. There were only gases and mud flows. Okay, so this is land, this is sea. So we merged onshore, this is the coastline, this is the coastline. So we merged onshore and offshore data, so we put away the water in order to see the whole topography of the island. Okay, and this is the main point. That's why this Erasmus is very important, because we are not distinguished the onshore-offshore. We need to merge the data and see the morphology and to identify the geohazards. For example, here we have a volcanic eruption for sure, but we have a lot of landslides around this volcano. Or here you can see this is Strongyli, a very small island, but you can see the top of the island here. This is on land, And if you see this island far away, you can see only a small cone. But if you map the area, you can see that this small cone started from 600 meter depth and coming up. So this is 600 meter depth, this is 120. So the height of this cone is almost 720 meters. Okay, so, and these are some other submarine volcanoes. So we merged the data, creating synthetic maps. This is Santorini. This is the famous island that you are here. Santorini, you have seen this slide, this figure. Santorini has 3 different types of geohazards. We have a lot of volcanoes. This is Colombo, submarine volcano. I will show you some videos. This is active fault zone. This is some of those faults that has been activated in 1956. So we have volcanic eruptions, fault zones, and a lot of landslides, even inside the caldera and outside the caldera. That's why we map the area, and also we merge onshore-offshore data to create this beautiful map. So, and then when you have this map, you are doing your morphological interpretation. So you can give this map, not the mathematic, but the interpreted map, the morphotectonic map, to the civil protection agencies, and you can inform them what are the geohazards of Santorini and where are the active fault zones. So that's why it's very important to map the seafloor. Okay, so this is some other examples of in the cruise that we had in 2013, 2012 with Marion Defense, the French vessel, and we mapped the Mid-Atlantic Ocean. These are ocean core complexes. In this area, there are some marine volcanoes. We saw a lot of pillow lavas. Unfortunately, we didn't see any submarine eruption.
Can you explain what the core complex is?
The ocean core complexes are some high mountains on the seafloor. Believe it, you are in the middle of Atlantic Ocean. Okay, so in this area, the 2 tectonic plates are taking apart. Okay, are moving away. Okay, so in this area, even though when we have mapped this area, we say, okay, now we are going to see the magma. Yes, okay, we are going to see a huge hole on the seafloor, and the magma will go up. No, this is not the point. Okay, this is not happening. The ocean core complexes are some small mountains, high mountains, sorry, that have been created because we have also some active fault zones, and one plate is moving down and up and then apart, and created these beautiful high mountains. And even though the depth there is 3,600 meters, the top of these mountains is almost 2,600, 1,800, so it depends. So why the people are exploring these ocean core complexes, because especially this slide, okay, these are the products that they are coming from the mantle up to the surface. So the petrologists, okay, the people that they need to do some petrological analysis, they explore this area and they are collecting samples because the rocks are from the mantle, not from the surface. Okay, so they like pentotite, gabbros, okay, diorite, and so on. So we mapped the area, and also we used AUV to identify. In this area, we found some black smokers, but we couldn't see the size of the black smokers using this kind of resolution. Okay, and I will show you what we did. Also, you can also have ROV. This is, we are in Santorini in 2017. Yeah, okay. This is Victor. No. What was the name of the Yomar? I don't remember the name of him. What? No, the name of the ROV, I don't remember. So, not the name of the person.
You said Victor.
Victor is the name actually of the ROV. So we are using ROV also to map the seafloor, because you can install the multi-beam system in the ROV, and you can be very close to the seafloor. So we did that in 2017. So you install, okay, you can do the SWAT bathymetry using resolution up to 50 meters, but if you want to be focused in a specific place and do a detailed mapping, you need to be close to the seafloor. And what we did, this is an ROV, we install a multi-beam system, and we can create either photomosaic using high resolution underwater mapping technique. We can create either photomosaic or multi-beam, or SWAP mapping in a resolution of centimeters or 1 meter, okay, to identify the morphology. And of course, in Colombo, we did that inside Colombo. This is Colombo. On the northeastern part, there is an active vent field, and we map this area using ROVs. And all these turtles, you can see, they isopod around here. All these points, the resolution is 1 meter, and all these points are chimneys. We dive there also with ROV, and we explore the area, and we say, okay, this point is a very huge chimney, or this point we identify that, of course, is another chimney, and so on. What else you can do with ROVs? If they have a camera, high resolution camera, you can do whatever you are doing, you have done when you have a camera on shore. What did you do when we are on the field? You took photos, okay? And what did you produce? A norm or a photomosaic, okay? We cannot do that when we are exploring the seafloor. So what the ROV is doing? The ROV, if you have a slope and you need to map the fault scarp, okay? You are doing a photomosaic using the camera of the ROV, and then you can produce. This is the scarp in the middle of Atlantic Ocean. This is a detachment fault zone, or this is the slope inside Colombo with the different layers of pumice, as you can recognize the pumice. You did exactly the same in the mine. Exactly, you produced this kind of picture. We also produce this kind of picture using ROVs. So we are doing photomosaic. Tell me. Yeah.
It's like a drone inside the
Yes, it's a drone, yeah, because you are using the ROV, and the ROV is doing this. Yeah. But it's very difficult because you are on the sea inside, you have a lot of currents, okay, and the pilots must be very, very careful, and also they need scientists to be in cooperation with them, because you need to tell them what to map and what kind of photos do you need. Otherwise, you cannot do anything. Okay. So yeah, like a smaller drone. This is a fault scarp in close to Guadeloupe. That has been activated, I think, in 2004, if I remember well. We published this data. So you can see this is a fault scarp. Okay. Exactly the same scarp that you can identify on shore. Okay, you know this guy, but at that time, 2 years before, it was from University of Bristol. We used this blue ROV in order to map the shallow hydrothermal system at the southern part of Milos. So we wanted to map the area that there were a lot of bubbles that were taken out. And it was better to use this kind of ROVs because you don't need a vessel. Yes, less money. Okay. And also what I explained in the morning, and also Alessandra will explain more, okay, you have high resolution, and the crucial point is that you map very close to the coastline, and you don't have a gap. Okay. So one of the products, you can see what Alphamas did today, okay, parallel lines, taking a lot of photos of what we did in Milos and produce a photomosaic and 3D model. But now we will be very, very happy. That was also an experiment for us to merge the drone data in the ROV data and produce a synthetic photomosaic onshore, offshore. That will be great. Also, that will be a product of Erasmus summer school. Okay, and of course, if you are lucky, yes, if you are lucky and you have somebody else to pay for you, like a German documentary, ZDF, they can bring a very special ROV, like a human, and we were in 2017, 16? Okay, I can't remember anymore how many cruises. We were inside Caldera, you can see the dikes just behind. So there was a documentary about, of course, Savini, of course, the Minoan eruption, of course. Okay, so what was the idea? The idea was this is from Canada, University of Canada. This robot is being used only for archaeological purposes because it has very delicate hands in order to take, to grab archaeological settlements and not the girls, okay? So this beautiful guy, okay, it was very funny, this beautiful guy has mapped the dikes. He was very close to the dikes, and there was another diver, and they were communicating, look at me, higher here, okay, so on, and we mapped the dikes in some parts of the dikes, also using some divers. This is very, very expensive, okay? This robot is up to, he can dive up to 100 meters, but now they told us that he can dive up to 500 meters. Okay, this is very, very expensive equipment. That's why we were so happy that the German government, the German television paid for this, for Ocean One, to have it here. So, what else are we using, except of ROVs and so on? We are using the technologies here. The technology is AUVs and gliders. These are autonomous underwater vehicles, so they use batteries, not electricity at all. Okay, and they map the seafloor in very detail in centimeters. They produce maps in centimeters because they are very, 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 very close to the seafloor. What is the disadvantage of using AUV? The disadvantage is that, okay, when the technician, when you are on board, they make a plan, they release the AUV, they leave it for 12 hours to do the mapping. You can have a coffee at that time on the board, but you cannot check the data. You will see the data when the AUV is on board. And if the AUV has a problem, you don't know it. And you miss 1 day. 1 day on board is it means a lot of money and waste of time. What we are going to do in December, when I will be on board Falcon, they have in Woodstock, they have produced they have established a new AUV that can gives you that sends in real time the data, so you can see if it's correct or not. So this is very, very important. And the other thing is that if you are exploring the seafloor that has a lot of different features, the AUVs are flying in a distance of this feature. These new gliders that we are going to test in Costa Rica, and then we will test it inside Colombo. These new gliders, if they find an obstacle, if they say, okay, this is happening, they are not grab the obstacle and move away, okay, they say, okay, now I need to be higher, and then move on, and then continue my map. Okay, this is very important. This is the new gliders and the new IUVs that Woodstock or MIT is using. Okay, so this is ABIS. We use ABIS also. This is a video from, it's okay. Yeah. We use ABIS from Geomar to map the seafloor in the middle of Atlantic Ocean at the depth of 3,600 meters. And we identified a lot of black smokers. And also, we use ABIS to map the northern part of the caldera in Santorini and also Colombo volcano. So you need to have, of course, big vessels. Okay, like Papuapa, this is Papuapa, the French vessel. And then, okay, you can see it here, it's moving. If it's playing, okay, look. And then blue. There is a rope with the vessel. Okay. The video is almost 2 minutes up, that's why fast. And it will be in the water. Okay, bye. Now you can have a coffee. That is a very nice time for us because we are feeling relaxing. The vessel cannot move and you cannot do anything else. It's great to have everybody on board. Yeah, for 12 hours, holidays. Okay, and it's moved along. Okay, now the rope has moved and moved along. Okay, so, this is one screen from the AUV desktop of how they are doing the mapping. And the bad thing is that they can cover a very narrow area not a large area because of the batteries. It's almost 12 hours. Every 12 hours, the AUV must be on the deck. Okay, and we used Abyss, and also we used the Girona, Alessandra. This is the Girona UV. This is only 500 meters, and this was mass spectrometer. So you can imagine that we are going to use only the other part, not this one. This is mass spectrometer. Okay, up to 500 meters. And we mapped the inside caldera, so you can compare the two data. These are the swath map of 20-meter resolution. This is also 20-meter resolution, and this is the resolution of 1 meter. So here, for example, you can see a lot of landslide scars here, or you can identify also some channels. And you can also see how steep are the offshore slopes of the Santorini. Okay, it's here in more detail. Look the morphology. This is 1 meter grid resolution, okay? Look at the channels. Or if there are some ridges, some small mounds. Of course, the AUV, you need lots of money to rent an AUV. Okay, this is some other examples of how we map the area in the Middle Atlantic Ocean, and we produce some more detailed maps and also find some black smokers. This is the axial, how they map the area in the axial seamount. This is very active submarine volcano of the western part of North America. This is the only place, one of the only places of the Earth that they are using ocean seafloor, online ocean seafloor observatory. So you are in front of your computer and you can watch what the robots or the AUVs are doing. So you can see the lines of AUV right here. Also here, in different details, in Nomikou Basin, with a resolution of almost 0.1 meters. So here also to compare, okay, this is SIP collected bathymetry at 20-meter resolution. This is AUV collected bathymetry at 1 meter resolution. So you can very easily, okay, see the difference of the seafloor features. But it's very difficult to use AUV. Okay, so we know that. Also, this is the AUV transect, because they wanted to map a very detailed landslide in this area. I will give you the presentation, but I don't want to, we have so many slides more. Okay, also we identified some volcanic domes on this area using AUV. So the first thing that you can do is to map the area using the SIP vessels multi-beam system, and then you mark some specific sites, and then when if you have an ROV or an AUV, you can map the area in more detail. This is how we are doing the seafloor mapping. Come on. Okay, that was the video. Sorry, I will give you the link. Okay, so this is the seafloor mapping. So you need first to map the area. Okay, then you need to identify what are the stratigraphy, or what are the sediments or the different layers below the seafloor. So you need to have seismic survey, and you are going to use it's like ultrasonography. Okay, you need to find out the baby that is beneath the seafloor. Okay, you can on shore you can do it very easily, because okay, if you are going and have some roads, some new roads, the geologists are very happy. Yes, because if you are having a new road, you can see the geological formations. Okay, here it's difficult to do that, so we are using air guns, okay, just to identify the formation beneath the seabed. So what is a reflector in general? So I will give you I know that you are not the expert, okay, just few slides on what is a reflector. So a seismic reflector is a boundary between beds with different properties. So there will be a change of lithology of fluid field from bed 1 to bed 2. So what we are trying to identify the different geological formations beneath the seabed. For example, we were there close to the beach and we say, okay, mineral deposits, rotary volcanic formations, peristera volcanic formations in general. So, using the seismic survey, we can say that, okay, this unit is unit 1, this is unit 2, and so on, and so on. Okay, for example, this is a seismic acquisition offshore, and you can make, depending on the size and the geometry of the seismic reflectors, you can have a different interpretation. Okay, this is more detailed. Or time versus depth, two-way time does not apply directly to the depth. Okay, so expensive instruments. You need to have a vessel. You have some airgun arrays, and these are reflected waves that have been stored in the hydrophone streamer. And hopefully, for the processing, you need seismic units. This is open software. But believe me, it's very, very difficult to know how to process the data. It needs lots of time, and most of the times, these people are not geologists, but they are geophysicians. Okay, they know a lot of mathematics and physics, except of geology. Okay, this is how we are doing the seismic survey, especially for the petroleum companies, because we are using lines of air guns, different kinds of air guns. So these are the sound waves. This is a specialized air gun, and you did the seismic survey. Also, okay, that was. So these are some reflectors that show us that, okay, we have a lot of volcanic cones with chaotic reflectors, this wide area. This is the area of sediments. So this is a small basin, for example. Or here is another cone. You can see that we don't have reflectors. Okay, this is a mud volcano. At the top is a mud volcano in the area, the southern part of Turkey, in Alessandra area. Or here there is a seismic profile of Nomikou, and I have told you that this is the eruption of 1650, but using the seismic survey, doing the seismic survey, we identified 4 others different volcanic eruptions. Okay, these are also some sediments. Or inside the caldera, this is the seismic profile inside caldera. So the people that they are doing the seismic interpretation, they try to identify different reflectors and looking also onshore of what is happening onshore. For example, this unit 1 are the volcanic products of the eruptions, of the most recent eruption. This is the Minion eruption, and this is the eruption of Nea Kameni. And a lot of landslides. But the Minion deposits have been buried at the depth of more than 200 meters below the seafloor. Okay, so the Minion deposits have been buried by recent sediments inside Santorini caldera. Or here is we have seen that here is Thirassia. We were just here. We were starting just here. Here's Thirassia, and this is Aspromisi, and this is Akrotiri. Let me see if I focus.
No, it's working.
Different. Okay. Yes. Oh, that's better. Okay, so you can see what I have told you early in the morning, that there were a huge collapse between Thirassia and Aspromisi and Akrotiri. So you can see the landslide scars here. The landslides over here. And these are a lot of volcanic material, volcanic domes. And also, this is the caldera rim, this is a huge collapse, and this is the west basin, that basin, here. And all of these, the yellow layer, are the pyroclastic flows that they are coming out, that are covering the outer flank of Santorini volcano. Difficult explanations. Or you play with the seismic reflectors and you can identify the faults here and different sediments inside a basin. Lots of fault zones, but the most important ones are the boundaries, the main ones, the main fault zones, like the Amorgos fault zone. And also, you can play with the 3D tectonic models when you have the seismic data. And for example, we measured the throw of this fault. It was 12 meters. That gave the 1956 earthquake. Also, here you can see a landslide. This is Nisiros. We mapped this area. We did the seismic survey. That was the fault zone that has been activated in 1997. Gives an earthquake of 5.7 and has produced a lot of landslides along this fault zone. Okay, this is the fault zone, and these are the landslide that has been produced due to that earthquake in Nisiros. Also, so you have the bathymetry, you have the SWAT map. The SWAT map, so these are the basins, okay, the blue. These are the active fault zones. You have dense isobats. Also, you can have a lot of landslides, like here, lots of landslides. And then in this area, you have a lot of underwater volcanoes, okay, like the Strongili. And so you are making the rotation, and then if you have the map, you can draw the lines, and you can produce a tectonic, and also a tectonic map. What the students of oceanography are doing, they have a SWAT map, and they try to develop the morphology. They try to identify the active fault zones using only the seafloor morphology. If you have also the seismic survey, that's okay. So you say, okay, this is an active fault zone because I have seen the throw, also the offset, also in the seismic profile. So we produced this kind of tectonic maps. Okay, orientation, population, so on, the length, and so on. Or these are another seismic profile. You see, you're starting from here, and you have different fault zones and a basin. Okay, so this is you complete an offshore survey. You have a SWAT map, and then you have a seismic profile, and then you draw the active fault zone. Or here's the basin. This is the first fault zone, basin, another fault zone, basin, another fault zone, and another fault zone at the end. The boundaries. This is the North Aegean Sea. Also here, this is the continuation of North Anatolian fault. This is a major fault zone in Greece. Okay, this fault is the northeast-southwest direction. It's the only place, one of the places in Greece that we have strike slip. Okay, so movement, and this is the seismic profile of the North Anatolian fault. Okay, so SWAT map, and then the interpretation is to produce a tectonic map. Why do you need to have this kind of tectonic maps? Because if you measure the length of the fault of the offshore, you know the magnitude of an earthquake. So you can give this kind of maps to the Civil Protection Agency and tell them that, okay, please build the houses more safely, for example. And in Greece, unfortunately, most of the times the earthquakes occurred onshore, so it is very, very essential to map the seafloor and to identify all the active fault zones. Okay, for example, in Santorini, we don't have an active fault zone, except of the Colombo line. Okay, this has to do also with the extension and the organic centers around that. But we have so many fault zones in the northeastern part. So if you don't map the area, you cannot have a view of the active tectonic fault. That's why this is a major hazard. This is the North Anatolian fault. This is the North Anatolian fault. Okay. So, a tectonic map, like this. Also, we are doing a synthetic map, identified also the basins, the subsidence, and the uplift of the seafloor. But the base of this is to have SWAT mapping. You have a SWAT map. Otherwise, you cannot produce this kind of maps. Or this is just published in Marine Geology. It's not under review anymore. Just published just yesterday. Okay, so we produced this Skiros island. We had an earthquake of magnitude 6.4. So we mapped the area and we produced a map showing where are the active fault zones. And we identified 11 fault zones that can give earthquake up to 8. Okay, not 6.4, but up to 8. Also, this is some swap map and slope map in the area between Crete and Kassos. We mapped the area because once upon a time there was a huge earthquake with a magnitude of 8.2 that created a huge tsunami that destroyed completely Alexandria in 1135. And also this kind of, these are the tectonic, the active fault zones that you can identify in the SWAT mapping. Or, this is a synthetic map. Okay, so the blue color are the basins, these are the active fault zones, and this is the area that you have landslides on the seafloor. Okay. And in 2015, the Proteus experiment, this is a Marcus Lancet, we deployed OBS. OBS is ocean bottom seismometers. Okay, seismometers. And and 26 land seismometers. And we did an active seismic experiment. Okay, these are the ocean bottom OBS around Santorini because we wanted to figure out the geometry of the magmatic chamber below Santorini and also the geometry of the magmatic chamber of Columbo volcano. So you can see this is active experiment. We produced at that time earthquakes with a magnitude of 1.5, 1.6, okay, for 26 days. Okay, I believe it was so hard to be on board and to feel the tremble every time, every 5 seconds. Okay, and these are some first results. This is Santorini. We used 36. We used 36 ergan. These are 4 lines, but below these lines there are 9 ergans on each line. So can you imagine the noise of 36 ergan? Okay, we were happy. We were very lucky because the weather was so good, like in the video. And also these are the paper that is submitted by EPCL. This is the first results. And you can see that these are the low velocity below on the seafloor of Nea Kameni, inside Nea Kameni, and in Christiana Basin and in Abydos Basin on the other part. And the Alpine Basin is high velocity. And also these are not even in preparation. This is how Ben, one of the PhD students of Nomikou, tried to identify the tectonic fault zones around Santorini using the seismic tomography. Okay, so the low velocity means that you have basins, and these are the areas of uplift. So that's it in an hour. That I'm trying to show you how difficult it is to map the seafloor, to use different kind of techniques, okay, and also to do seismic survey, because if you want the new idea starting from Southampton, okay, from UK, is that when we are in Tasmania, they say that is that, okay, we don't need to do seismic survey. We don't need guns, because we have also a lot of problems with mammals and so on, and you can produce tectonic maps only using the seafloor morphology. This is the new idea of Southampton. Okay, things are very simple if you are mapping Atlantic Ocean or Pacific Ocean, because you can also produce geological seafloor offshore geological map, because you know that there are 3, 4, 5 different volcanic geological formations. That's okay. But if you are in the Mediterranean Sea, if you are in Greece, for example, or in Italy, and you have more than 100 tectonic units, geological units, I don't know how many, and you try to identify it and create a geological map, and if you produce a tectonic map without taking account the seismic profiles and present the geological map in a conference, they will kill you immediately. They cannot accept that using only the seafloor morphology, you can identify it and you can say that this is an active fault zone. You need to have seismic profiles to see the offset Okay, but in Atlantic Ocean, in the Pacific, they saw us some geological, offshore geological, marine geological maps without using any seismic profile. But this is Atlantic and Pacific, not Aegean Sea, not close to Italy, too many geological units. Okay, so this is for me, and Alessandra will continue.
So the presentation deals with the title is Integration of Remote Onshore, Onshore and Offshore Data in Geomorphological Mapping for Geohazard Assessment. And I really thank you, Heidi, for her presentation because introduced a lot of issues and instruments, especially kind of data that are really useful to collect information in marine environment for geohazard assessment. We will see how to integrate or which are the data that you need to collect to integrate data from land to the offshore domain in order to do geomorphological mapping every day. And here just a short outline. I did a brief introduction regarding marine geohazard because it's actually a topic on which I would like to tell you just two main things that I think would be interesting. And then we will see which kind of remote data are fundamental for geomorphological mapping in marine environment, but you already did what you mean. And the main data source that you have to search for collect information on elevation data for the onshore, offshore, and the critical nearshore domain. We will see how what we mean when we say is critical, the nearshore domain. And so, generally, marine geohazard is referred as a physical, as all those physical processes and related effects that have the potential to adversely impact human life and infrastructures, thus leading to a situation of risk. In marine environment, if you refer to marine environment and to your classical perception of what it is a geohazard, probably you immediately think to earthquakes or some landslide that can produce tsunami waves and so impact the coastline and create damage for our human society or human life. But actually, within the marine environment now, it's not the right button, sorry. Within the marine environment now we have actually a lot of activity, and especially industry is working faster and faster and larger in marine environment, not only for oil and gas production, but even searching for renewable research such as, for example, wind farm, but not only wind farms. Industry is also searching for other kind of resources. Seabed mining is becoming a very big topic of interest for industry in marine environment. So every time you have to work in a marine environment, you have to compile not only geomorphological map, you have to compile not only an environmental impact assessment, but also a geohazard assessment. So basically, industry provides a site-specific assessment of geohazard. So any kind of infrastructure or facilities that need to be built in a marine environment need deep work before to assess the geohazard. And for industry, geohazard are those which will cause problems during the installation of the structure, and thus which will present a risk to the structure during its operating life. And so there are not only landslides or earthquakes and so on, but there are also big current, for example, that can accumulate sediment or eroded sediment close to the infrastructure, and then the structure can break down. Or even benthic habitats, for example, the industry considers sensitive benthic habitats a geohazard, because if there is an habitat to be protected, they cannot build anything. So anything that is deal with that can cause problems during installation or during the life or the infrastructure is a geohazard for the industry. And potential geohazard are at a larger scale than encountered onshore and include, for example, also deep canyons. Canyons are able to have a retrogressive behavior and so hit the continental shelf and go toward the coastline. For example, if you build a communication cable that can cross a canyon, turbidity currents can arrive and break down the cable. So there are a lot of phenomena actually in the marine environment. This is a very simple sketch. And you have to imagine that in the future, the seafloor will be really a place where a lot of infrastructure will be built, because there are not only communication cable, gas pipelines, there will be also places in which you can, for example, storage your energy product, oil or other kind of electrical energy. So it will become really a world colonized by us, and so we will need very detailed geomorphological map. And for the scientific community, basically many research projects designed for define marine geohazard are essentially considered seafloor mapping projects. So you need to use the instrument that Evie presented before, and so provide this geological geomorphological map. The two words, terrestrial geologist and marine geology, actually since few years ago, stay really separated, so they do not communicate a lot between them. A lot of marine geologists take information from terrestrial geologists, for example, especially for the terminology, but a lot of discoveries and revolution in geology came from marine geology. If you think that the first map of the seafloor give us the knowledge about the tectonic movement, so marine geology was the map of the seafloor was really important for the world geological world, essentially. But this communication is still difficult, and probably it's the nearshore that can give us in the future some opportunity to better communicate between the two worlds. And so, sorry, okay. So let's start to see some example. As Heavy told at the end of the presentation, our seafloor environment in the Mediterranean Sea is very complex. So if you get this bathymetric map, you can appreciate the complexity of the seafloor. For sure, you see a lot of structures, scars, landslide canyons, tectonic alignment, volcanic edifices. This is a region in the Mediterranean Sea, in the southern part of Italy, but in Greek you also have a lot of complex seafloor, and we know very well which are geohazards related to landslide and also submarine landslide or volcanic eruptions. So we share more or less the same problems. And I just reported here some example related to less common, to a not common perception of what is a geohazard for the marine environment. For example, canyons. Here we are in the Strait of Messina, between Sicily and Calabria, and close to Reggio Calabria we have both an harbor and an airport. But as you can see from the summative metrimetry, we have a number of canyons that are eroding the continental margins, and the heads of the canyon are very close to the coastline and provide some damages in the past. This is an example of the Gioia Tauro harbor, that is the biggest harbor in the Mediterranean, where all biggest ships arrive with containers and then distribute containers to other smaller ships. And as you can see, there are two canyons that have a retrogressive behavior toward the coastlines. And in 1977, there was an earthquake that generated landslides, and the landslides basically destroyed part of this harbor without any damage for people. But 2 years later, in 1979, in Nice, France, there was the same situation. A head canyon failed down, and a big part of the harbor failed with the canyon head, and 2 people dead actually for this accident. So why? Because we built in a marine environment without knowing what there is underwater and which are the processes acting on the marine environment, because you do not have only to know the morphology. If you find a canyon, you have to check the canyon is active, how much is active, there are turbidity, hypertechnical flow that erode the canyon or not. So you have to see what happened on land and which is the relationship with the canyons that you find on the seafloor. And you have also to do geotechnical measurement to see the stability of the soil and so on. And this was another very big accident occurred in 1783 in Scilla, Italy. Scilla is always on the southern Calabrian margin coastline, very close to Messina. Sorry. And there was a number of earthquakes on 5 February, especially 6 and 7 February in 1783. After the first earthquake, the people living here in a little town close to the Campana mountain left their home because the earthquake was quite big, and they set up tents on the beach here. But the night just after the first big earthquakes, another earthquake occurred and triggered a landslide. And the landslide triggered the tsunami waves, and 1,500 people died because the tsunami will destroy all the tents that were they set up on the beach. So this was a bad situation that occurred here in Scilla. And as you can see here, this is the Kampala mountain, the scar drawn on the flank of the sea. And the bathymetry is not so nice, was collected a few years ago with a not so good system, but you can happily say that there is a bigger glide scar here and some blocks representing the main place in which the deposit fell down. And so geologists thought that actually there was already an instability that was really clear at sea, and probably the landslide set up where the instability was already marked by this old slide scar. So a knowledge that could be useful at the time. Here I just report this last example from Ischia. You know that the flank of volcanoes are subject to collapse, and we have a very typical example for our Ischia highlands, where there is the southern flanks that fade down and provide this very large failure scar that you can recognize even at sea. And this collapse triggered a very big debris avalanche. Volcanic highlands are the main feature at sea that are able to provide debris avalanches. And take care that debris avalanches are the biggest deposit on land and not the biggest deposit at sea, because at sea, if you mention the margin, continental margin, sediments are quite homogeneous. No? The stratification in most of the cases is quite homogeneous. If some slide scar occur, it can really affect a very large portion of the margin. Some biggest landslides at sea are larger as the entire United Kingdom. So there are very big movements at sea when a slide occurs. Debris avalanche is also important, but not so important in some cases as other bigger slides. But in any case, for any debris avalanche, for any volcanic island that you can map, it's very common to find this kind of feature. Here you have the bathymetry. The scar on land is this one, but you can identify lateral scars even on the bathymetry, and here you can trace the scars on the seafloor provided by the glide of these big blocks of rocks that were part of the debris avalanche and then of the debris flow. In the seismic profile also you can see the deposit with the blocks. And as I anticipated you before, canyons are important to map and to understand. With understand, I mean you have to know if they are active and which kind of relationships they have with the land, with the river that delivers sediment into the canyon or not, but also with the littoral current. They are also important, for example, if you are studying the erosional processes on a beach. If you are on a coastline like that one, and sediment are provided by littoral currents, for example, and the littoral currents goes into the canyon, they actually supply sediment to the canyon and not to the beach. So it is very important to understand relationships, all relationships that canyon has with the processes occurring on the shelf and with the catchment area on land. Here, another example in Calabria of three main canyons we have on the Ionian margin, this time on the Tyrrhenian margin. And you can see here these three main canyons that are very, very close to the coastline. The end of the canyon is 50 meters far from the coastline, so really attached to the coastline. And they start to present very peculiar morphology when they are so close to the coastline, such as this one in the center that is called Gioiosa Canyon. If you see, it reached the coastline basically and start to enlarge and assume this kind of fan-shaped head with a lot of growth. Sorry, the light is not so illuminated the image, but there are a lot of gullies, incision on the head of this canyon that testify a continuous delivering of sediment from the river to the canyon.
Is there a town on the coast? Just
Yes, there are a town, there are real train, and streets, and so on. So it's not a so good situation actually.
So putting a town there, does that stop the sediment supply to the canyon? Or is the sediment
no,
channels?
actually, I think that stop the sediment supply should be not a, I would understand your question.
I'm just wondering if you put coastal defences, for example.
No, there are no any particular structure to defend the coast from the erosion. I guess that to my opinion, I make the area totally empty of people and see what happens in the future, because I didn't show to student the profile, but you have a very step profile. It seems that more or less it will be cut away the step. Okay, so, but came back to the beginning. Why onshore and offshore interaction are still occasional? Basically, it's not the fault of anyone, but it's because mainly there are different methods and techniques to explore, so you have to become expertise with different methods and techniques, and so at the beginning you work in your world and do not communicate with other world. So, and in most of the case, there is also the lack of reliable data to efficiently join information and knowledge between the two words. But, for example, the collection of nearshore data could be, to my opinion, instrumental to foster interaction and know-how exchange between terrestrial geomorphology and marine geomorphology. So, what we mean in the title when I cited onshore, nearshore, and offshore remote data, I do not want to refer to specific literature terminologies, but just to understand what we mean. Onshore, I mean all data that are totally not related to the marine environment, so above the high tide line, basically towards the land. The offshore is all the submerged landform, generally deeper than the wave-based level. What is the wave-based level? The wave-based level is indicated in general as the half of the mean wave that affect the coastline, and the half of the wavelength of the wave is the depth at which you do not still have movement of sediment provided by the waves. So the area between the coastline and the wave base is the area in which you have the sediment that can be moved by water movement, by wave movement, sorry, because also big current can be water movement. the action of the waves close to the coastline refer especially to this area, no? In which the wave is able to move the sediment and generally define the coastal zone explored by geomorphologists. Obviously, there is no specific position to distinguish in our presentation the nearshore from the offshore. The wave base is always taken into account in book of geomorphology with this meaning. Now, basically here we refer to the area in which it is difficult, and we will see why, collect data with the same technology used offshore or with the same technology used onshore. But at the end, the nearshore is also central to any kind of coastal study. Is the, as I said before, is the area in which waves can move sediment, in which a lot of processes occur, and have also there are also short-term changes in this area because the waves can change the profile of a beach, for example, in one day. There are tides, wave, currents, movement of sediment is important, and coastal changes are very dynamic. But at the end is also the area in which geohazard assessment need to be done effectively. And so let's have a look to which kind of data you have to provide for to provide geological geomorphological map. Basically, you have to collect if you want to integrate the data onshore, nearshore, as I said before, and offshore data. At the base of all information, you have to collect the topography. On land, the topography is more or less already collected at quite good resolution, at least 30 meters we have for basically most part of our Earth surface. And the problem is the offshore and the nearshore. For the offshore, we have the technology. We saw the use of multibeam as instrumental to collect bathymetry. As we will see after, actually, we have raw knowledge about the seafloor topography. I mean that we have a lot of work to do when we think to high resolution data, so those data collected by multibeam system. For the nearshore, we are at the beginning. So we are collecting reliable data in the nearshore zone just now, reliable elevation data just now. Regarding, obviously, to provide a geomorphological or a geological map, you need other remote data, such as the nature of the sediment, not only the elevation that gives you the topography, but we need also to know the nature of material, sediment, rocks that occur. So on land, we use classical remote sensing technique, so the satellite that collect data and you study the spectrum signature, and so you study hyperspectral or multispectral bands collected regarding the surface. For the offshore, we need the scattering, and nowadays you can collect the scattering together with multibeam, or you can use other instruments to collect this kind of backscattering. The scattering is the energy provided by the seafloor that you can correlate to the type of sediment, if there are fine sediment or coarse sediment or outcrop or some other feature. So it's the only information that we have now to have an idea about the component. Then you obviously need always to sample and to have ground control measurement to calibrate even onshore and offshore your data, your remote data. Okay. And for the nearshore, so far we use the remote the classical remote satellite remote sensing or aerial photogrammetry, but not the seafloor scattering, and we will see after why. Then obviously to provide a geological map you need seismic, and there are traditional techniques for the onshore domain, the offshore domain. And for the nearshore, you can actually use geoelectric or some stuff. I'm not expert on it, but it is more easier. It is easier to collect seismic data than bathymetry data in the nearshore. Sure, and then you can provide your geological map and collect our data. If you look in detail, now we deal especially with the topic of the topography, which is the base of your information. No? So, basically, if you want the topography, you need to provide what we call digital elevation model. I just put here some indication regarding terminology. Remember that when you use DIM, then I do not know in English how it is the correct pronunciation. DIM or DEM? DEM, or even in English, DEM. Yeah? Okay. Then is an elevation model of work. Their topography. So remember always point one that is a model. It's not the reality, it's a model. And a model that can change, especially regarding resolution. The DSN, sometimes you can also find this acronym that is Digital Surface Model, which is the difference. The Digital Surface Model takes into account even vegetation, buildings, and so on. The true DEM, Digital Elevation Model, should take into account only the earth-bare topography. The digital terrain model is the most similar to the DEM. So DEM can be strictly compared to DTM, Digital Terrain Model, but it should not be considered a digital surface model. So remember, when you are providing topographic map with your with photogrammetry using the drone imagery, your final DEM is actually a digital surface model. Because you are not able to take out vegetation and other structures from when you use photogrammetry. And this is the main difference between using a LiDAR system and photogrammetry. The LiDAR give you actually the true DEM, the true digital elevation model. It's able to cut off the vegetation, for example. So this was just for terminology. So the DEM is a model that approximates the nature, the Earth surface and its nominal ground. And this model can be different, so you can have different model of the same surface, can be different concerning the purpose of use, and this depends on the person that did the model, but especially can be different regarding the quality of data sources. Remember also that any model with which you will deal cannot tell you always the truth. So, not all models are trustworthy. So, and they can change one from the other one regarding also the interpolation algorithm. They do not have the time, but when you provide a model, you actually take some data, and data are processed by algorithms. So there are many kinds of algorithms, basically. You have the data source, elevation, you collect elevation data with different density, with different accuracy. And when you want to deal with the accuracy and when you want to know how much is close to the reality, your model, you have to know all the process and all these feature, all these all technical part regarding also the technique to collect the data. And then also the experience of operator is important, obviously, both for the part of acquisition and the part of processing of the data. So at the end, any model can be different from the other one. I believe that if you yesterday collected the same photo on the same wall and you process correctly the data, probably each model could be different. Collected also the photo in a different way, okay? So the operator sometimes is critical to have good data. So now just a brief review on how you can produce digital elevation model for the onshore part. Once the first models were produced using a topographic map collected very manually, basically. Why they did this opposite process? Because at the beginning we discovered, the scientific community discovered how was easy and fruitful work with the model that I can visualize in 3 dimensions. I can apply algorithm to see the flat area, the incision, all the topography, and explore the topography in a quantitative way, that is terrain analysis. So all terrain analysis feature, procedure can be done on a model and not on a topographic map. So at the beginning they transformed the topographic map into models and started to work on models. But now we have basically good technique to collect data that can be used to provide the model. The first one was the ground survey technique using GPS and DGPS, and now we do it just for very little area because it takes a long time. You have to collect each point and so you count for a larger area. There is an increased use of digital photogrammetry, as you know, as you experienced already, thanks to the use of drones, especially, no? Because before the technique started with aerial photography, but now we have drones, so we can collect easily a lot of data and process them and have this model. But there are also, and as I told you before, if you want a true DEM and not a digital surface model, you have actually to collect the data, for example, by satellite or aerial platform that use the LIDAR system. Basically, what the revolution was related to the fact that these technologies are able to provide 3D clouds, point clouds of measurement. No? So the world of 3D point clouds technology is the most advanced in the production of elevation data. What you used yesterday is the electro-optical system that is the photogrammetry. But then we have also the active laser imaging system, the synthetic aperture radar system that are able, as I said before, to provide the true DEM and not digital surface model. Here I just reported some tables taken from literature, just to show you that there are a lot of sources in which actually you can find onshore topographic data at quite good resolution. You can find free data at least at 30 meter of resolution. 30 meter, I mean the size of the grid cell of your digital elevation model. And this is great because this kind of data at this resolution for the seafloor environment we have just for the 4% of the seafloor, of the world seafloor. So it is really amazing that you have it for the wall and surface. And remember also the what we mean with different resolutions. So basically at low resolution we have data also for the seafloor. We miss the high resolution. And for the onshore data, the high resolution can be reached only by LIDAR or by drone. But as I said before, if you want precise DTN, you need to use LIDAR. For the offshore domain, as I said before, we know generally at low resolution the wall seafloor topography, but this is a topography that has been collected thanks to the use of gravimetry on satellite system. Yes, gravimetry data can give you information about the topography because it's dependent on the topography. And so we have the total map into satellite system. But if you want detailed information, as Heidi explained you need multi-beam system. And this is a new map, not so new now, but this is a map that you can find in literature provided by Becker et al. In 2009 that collected both satellite data and mixed it with available multi-beam data and provided this SRTM30 plus is called, and this is the most resoluted map we have so far for the entire seafloor. Here you can appreciate the track lines made by vessels that collected sounding measurement directly with the multi-beam system offshore. They look so much, but actually it's only a question of scale of representation. They basically represent the 4% of the seafloor, the sounding that we have collected so far with multi-beam system. So we have still a lot of work to do. And now, just for your information, I put here also a reference to EMODNet. EMODNet is a free portal that you can find on internet. It's a European Marine Observation and Data Network that is trying to collect all data coming from the seafloor and in order to distribute all this data to the scientific community or to people that would like to do useful research at sea. And there is also a part, obviously, the first layer is the topography, the bathymetry. And here, if you are a scientist working at sea, basically you can collect your data and then keep contact with EMODNet and deliver your data. So any other people that will need your data has to put in contact with you and ask permission to use the data and blah, blah, blah. This is in general how it works. Okay. So, regarding multi-beam system, and before introducing the critical part of the nearshore zone, I would like to remember you that since the multi-beam system collect data working on this fun sector, or on this sector of, it works on a fixed angle, and the angle depending on the kind of system can go from 120 to 150 degree basically. And it can emit a number of beams, each sounding collected, each depth measurement collected on the seafloor is called sounding, and is collected by a beam, an acoustic beam, so that's why it's called multi-beam. And also the number of beam is different from one model to another, and the resolution can be different, but as I told you before, more higher is the frequency, more resolution you have, but you need to work in a shallow environment. If you need to work in a deep environment, you have to work with a lower resolution and you lose, with a lower frequency and you lose resolution. But the important point is that when the bathymetry decreased and the depth and the environment became very shallow, as you can see from the picture, the area covered by your fan is reduced. So if you want to cover, okay, this is another picture just to remember you that when you provide a dam, it means that in every single cell of the dam, there are a number of sounding collected in that way. So the average between the sounding gives the value of the single cell, the zeta of the XY zeta information. And so, as I anticipated you, when you work with a multi-beam, the coverage respect the seafloor depend on the water depth. And here there's a picture in which, if you consider one ship time day, so 24 hours of work of your vessel, if you work at 3,000 meters of water depth, you are able to collect an area bigger like this. This is a scale of 50 kilometers. So you are able to collect 50 per 50 kilometers in 24 hours. If you reduce the depth and you go at 2,000 meters of water depth, the area decreases significantly. And then if you go on 1,000 meter depth, again the area covered at the same time in 1 day decrease, and exceptionally decrease when you work at 100 meters of water depth, because it means that you need to do a track lines and the other track lines that need to be in overlay with the adjacent line in a very short distance.
But the resolution doesn't change.
Actually, also the resolution change. This is just to explain you the coverage, the topic of the coverage per day regarding how much seafloor you can cover with the system. The truth is that if you work at 3000 water depth, you need 12 or 24 kilohertz frequency. If you work at 1000 meter, it's better that you use a 50 kilohertz frequency multi-beam. So actually you have also to choose different system according to the depth. There are systems that are able to collect data even at 100 meter depth down to 3000 meter depth. Okay, if you work for example with a 24 kilohertz system, you can collect 100 bathymetry at 100 meter of water depth, but the resolution is not so good as a high frequency multi-beam system. So the resolution in any case increase when the depth decrease. Because you see also from this picture that if you consider the circle, what we call the footprint is little here than here. So more is the depth, and bigger is the footprint, and so lower the resolution. And here 100 meter depth, and here 10 meter depth, so nothing. 24 hours for quite nothing covered by the multi-beam system compared to 100 meter or 1000 meter of water depth. So it is not only a question of difficulties, because you have also to consider that the echo sounder need to stay submerged in the water environment at least 1 meter. 3 meter is better, and so just you lose this from 1 to 3, you lose that. You cannot use a multi-beam system because you do not have the space to use it. And from 3 to 10, basically you have to do many lines, and it's a very long and cost work. And this is just a graph that make your relation the depth of the survey with the multi-beam with the cost. So increase the depth, increase in a crazy way the cost. Just because, as Ellie told you before, you have to pay the vessel per day. And so you have to multiply the day for the cost per day.
You have to
But
find
not
another
only.
way.
Sorry?
You have to find another way to do it.
Yes, you have to find another way, definitely. And the cost is water depth dependent, the risk also is water depth dependent as well. We saw that the nearshore actually is a critical area in which you need to collect data to do a good geohazard assessment. And now the nearshore is also important for charting, for the safety of navigation, for construction, because now we are building harbors and all of many infrastructure on the coast and so on. And for the geohazard assessment, I also would like to make known that it is important not only to understand the geology of your area, but even more important is for the development of the modeling that can predict in some way the tsunami waves, for example. Tsunami modeling is quite an important topic in geohazard studies, no? And also risk and vulnerability assessment is an important topic that can benefit from the collection of data from the onshore to the offshore domain continuously. So now what we can do to collect data in the nearshore, basically we cannot use the multi-beam system between 1 and 7, 8 meter, basically. And when you are at 8 meter, 10 meter or 20 meter, the costs are high. There are many safety issues if the seafloor is not flat, because if there are some outcrops, you can damage your instrument or your boat, and so sometimes there is the inoperability also. But you can actually collect good data also with the airborne LIDAR bathymetry. There's always a LIDAR, such as the one used onshore, but technically there are some differences. And now I not list them, but it is designed for the water environment. And as you can see here, Here there is a picture of the coverage of the seafloor provided by the vessel and the coverage provided by the airboat. But it's the same. Logic. No, the airborne is higher, so the coverage increases. So how we can collect elevation data in the nearshore? For sure, with airborne lidar bathymetry. But it has actually high cost because you have to pay now the airplane and not the vessel. And the system also, the lidar bathymetry system is quite expensive. The satellite radar bathymetry is a new way to collect bathymetric data in the nearshore area, but is still in progress. What they do is something very similar to photogrammetry, but actually they apply algorithm to the visible images collected by satellite, even the one of highest resolution between 10 and 30 meters. The topic is that more is the depth, deeper is the seafloor, and more you lose, more there is absorption of the wavelength. So the change of the color is correlated to the depth. But in many cases, and especially in the nearshore environment, you can have rock, you can have sediment, you can have seagrass, you can have very complex environment. And so actually you have to determine which kind of material you have and then apply the algorithm related to the depth. The change of color associated to the depth. It's not so easy. If you have sand, white sand, for example, covering all the nearshore, it's very simple and it works very good. But if you have a complex environment, as it is in most of the case situation, we still do not have the right algorithms that can provide a good bathymetry. But it's in progress. So many companies deliver satellite, what is called satellite-derived bathymetry. And now we are experimenting that is really that is really cheaper than the use of an airborne lidar bathymetry, the aerial imagery processed by instructor for motion. Because in those cases in which you have very transparent water, actually the same technique that you yesterday used on land can be used for the seafloor. Obviously, only in those cases in which you have a very high transparent water. There are a number of situations that limit the use both of the airborne lidar bathymetry and the drone surveys, and especially is the coastal and the type of coastal environment. So I'm very happy to use both lidar and drone survey here, where there is a high water transparency, and those features on the seafloor can be seen also by my eye. Okay, but this is not the good situation in which you can use neither the drone or the airborne lidar bathymetry. Even the airborne lidar bathymetry is heavily affected by turbidity. Okay, when you have a high quantity of sediment in seawater, can be very difficult to collect reliable data. So basically, it's a type of cost, rocky versus depositional, etc., that strictly affect methods and technique of elevation data collection in the near shore. If you have, for example, a delta system, delta environment full of sediment all around, it's very difficult to use this kind of techniques. Even it can be extremely interesting because you can study with a very high detail the morphodynamics of this kind of environment. And even if you have a coastline affected by important swells for 6 months or for all the years, is very difficult because even the breaking waves affect a lot the picture that you are able to collect. So you need transparent and calm water, not only transparent, basically. So even in this case, this could be a coast, a Greek coast or an Italian coast. Probably the water are transparent, but if in most of the case the sea is rough or provide waves, you cannot do any kind of lidar or drone survey. The marine tropical environment actually are one of the environments in which you can collect good data, both for with the leader and with the drone survey. Because here, water movement is provided mainly by, especially within the lagoon system, is provided mainly by currents and tidal currents. You have big waves only offshore the reef, the reef crest. And so if you want to map the near shore, that is the flat area of the reef, actually here there are a lot of studies that are now using drone survey to provide bathymetry. And this is an area in which we didn't have bathymetry until yesterday. And the drone really did quite a revolution for this study. And this is just a slide that can resume a bit that the near shore area, so the shallower area, and the dynamic of the area is driven by the type of coast that you have. And basically, so geomorphologically speaking, that by the process that you have, the behavior of the waves, the tide, the currents, the sediment dynamic, and also the biotic processes are all processes that can determine if you can or cannot use this kind of technology. And even the extension, the topography, if you have a quite flat area, it's very good to collect data with a drone. But if you have a quite vertical wall, you cannot. In this case, if you have, for example, a cliff, a plunging cliff, the best is use the multi-beam system oriented toward the coastline, for example. Not on the seafloor, but toward the coastline. You can stay even 50 meters far and you can map all the cliff in this way in the case of a rocky coast, obviously. But if you are probably you already thought that the most difficult places in which you can have a reliable bathymetry are all the beaches, in which you have waves, in which you can have sediment, in which you can have either sun reflection, for example, and so. Okay, leader is expensive. It could be extremely useful to use the drone, but you have really to choose the right moment. So, and you are not always on the field able to collect data, no? So when you can actually use the aerial imagery processed by stratoform motion, when the nearshore zone must be is gently sloping or not too steep. Okay, so you can actually collect a very large area with your drone. When the water transparency must be high. Significant water movement must be absent, so you cannot have waves because the breaking waves cannot allow the electromagnetic wave to reach the seafloor. And no sun reflection at the sea surface. And as I said before, these are not good environments in which you can use the drone imagery. Here there is an example of drone imagery collected in Sicily. And as you can see here, there is a slide. This is a work of this summer. We collected the data just in July, so we are starting to work on this active landslide, coastal landslide. Here is the dam derived from the acquisition by the drone survey, and you can appreciate here the detail of the slide skirt. This is an abandoned village. Okay. It was a touristic village, now it's not working because they built it exactly on the fractures. Okay. And this is the tail of the near shore. Basically, there were a calm sea, but not so calm. We captured here the breaking wave zone. So here there was too noise to process in a correct way the data. But actually, the part between the coastline and for 2 meters was quite nice collected. And this is just an example. As I said you before, the best environment in which you can use such kind of technology is the coral reef environment, because there are these large flat area that are called flat area. Yes, this part is the geomorphological explanation of a reef. There is the flat area, and what is interesting is that for all the coral reef environment of the world, we didn't have reliable bathymetry since few years ago, thanks to the use of this technique, because any kind of vessel can navigate with a multi-beam system, can navigate inside this flat area. The satellite derived bathymetry has some difficulties, even if they were able to provide good data for the Great Barrier Reef. It was one of the first, but it went in the case, in some cases, such as this one, in which you have phanerogams, coral rubbles, sandy clays, and many kind of sediment on the seafloor, and many kind of different kind of reefs. Actually, it's not useful to use the satellite derived bathymetry, but you can provide all the shallow water bathymetry with the drones, and this is what we did here in Maldives. This is the Fafo Atoll and the Magudu Highlands, where we have a research center here. And we basically collect the data each October. Now there is my PhD student there, and each March and February. And so in this way we can also monitor the changes of the environment. Remember that for this environment, one of the biggest geohazard is the sea level rise. And so we are monitoring, if you monitor the morphodynamic of the coastline, the movement of sediment, you can understand if the situation is in erosion or is stable and so on. So here just some information regarding the procedure or the protocol. Our enemies when we work, because they really attack the drones, so we have to choose the right period, also according to the behavior of these birds. And basically the control environmental conditions are the sun low on the horizon, low tide situation, because we have also to measure the different temporal acquisition, and controlled wind condition to avoid distortion from water motion, especially. As I said before, even in this case you can have in some cases water motion that can affect compromise the quality of the data. So far we are monitoring the situation of these Magudu Highlands and also another highlands, another atoll. Just some detail, centimeter resolution. You collect the data, you build the ortho mosaic as you did yesterday, exactly in the same way, and at the end you have your depth. In this case, it is the real topography of sea, so we can call it depth. It uses the crest of the reef and the flat area. And it seems that this technique for this environment has a number of applications, because the geomorphologists, for example, study this environment that are remote, difficult to explore, blah blah blah. With this model, you can actually appreciate in a better way all the morphodynamic of these islands. In this island, for example, you see all the accretionary and sedimentary deposits that enlarge probably the island when there's a formation of the reefs. But here you can also see the problem of the wave, of the sea surface when there is rough, when there is a big rough. And here is the temporal change of little spit that we have on one island between March, April, and November 2017, and the dam derived from the ortho mosaic. Okay, I finished.